Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor IARE, Hyderabad. So in previous video we had seen about the one more method, that is Rayleigh wrist method. In this video we will see the total potential energy method and flexibility method. Okay, so let's see the topic we will cover in this one is the total potential energy method, and next one is the flexibility method. So first we will see the total potential energy method. Okay, so see. In the unrestrained spring mass system, unrestrained. So here just see, just whatever the spring actual size is there, that is there. In that, the mass is suspended. So this is the unrestrained system, unrestrained spring mass system. That is shown in figure A. The potential energy of the mass is normally defined as the product of its weight, right? That is mg, and height. So because of this, what is the potential energy in this case? That will be mg. This is weight into height. What is height here? H. So what will be the potential energy in this case? Mg H. Okay, that is for unrestrained one. Now when strained is there, so above some arbitrarily fixed datum. So above whatever this is there, this is the datum point, and that is at some certain height from the datum is H. If this will be here, this just whatever the normal mass is there, or just you are considering datum here itself, then in this case also the potential energy will be 0. So that system must be at some certain height. What is the height? Based on that only they will have the potential energy. Okay, so in other words, it has energy because of its position. So because of the datum only, that is the potential energy only defined by virtue of position. So with the position only they will have that energy, and that is called that as potential energy. Okay, now the mass has lost mgy of the potential energy after deflection to an equilibrium state. So mg into y. So just see here what happened first here when this was here. This is earlier mgh was there. Now it's getting deflected or strained by y, right? So now what is this difference? That is here. This is h minus y, right? So what will be the new one? Mg into h minus y. So at this position they have the energy mg h minus y. So just expand this one. So mg h minus mg y, right? Mg h having initially at this point without deflection, how much it's getting loose or lost? Mg y. So at this point it is having mg h minus mg y. So by what amount it's decreased? By mgy. So that is here only. The mass has lost mgy, right? This mgy of the potential energy after deflection to equilibrium state. So from equilibrium state, once it's deflected by y distance, that will lose mgy potential energy. Okay. So as a result, what happened? Deflection is associated with a loss of potential energy. So once deflection will be there, means their loss will be there. So loss in potential energy. Alternatively, we could argue that gravitational force acting on the mass causes it to move, resulting in a loss of energy. Now what happened in this figure? They have the mass, right? Now G also is there, so that mass becomes weight. So because of G also, this will try to, or gravitational force will try to pull this one. So because of that also, this will have some strain. This will get displaced here. So whatever the displacement will be there, that will be the loss of potential energy. So see, a gravitational force acting on the mass causes it to move, resulting in a loss of energy. So what happened? Because of gravitational energy, this will move down only. It's not like that this will move up. If this will move up, then potential energy will increase because now mass will be here, and this distance will be total h plus y. So once we will compress this one by applying the force here, if this will reach here, then they will have the more potential energy. But what happened? Because of the gravitational force, it's coming down. So this h is getting decreased. H is getting decreased means potential energy is lost, resulting in a loss of energy. Using this reasoning and assuming that the potential energy of the system is 0 in the unloaded state. So when the potential that is unloaded state, that time what we are assuming, that potential energy is 0 because mass is not there. Mass is not there, so potential energy is 0. Okay. The loss of potential energy of the load P as it produces a deflection Y is Py. That's right. Their mass we have here now and load P we are applying. So that P equals to mg. So here we are applying load P. So load into deflection is the only potential energy. So that P into Y. Where P is what? Mg. That is the weight, or you can say load. Thus in the deflected equilibrium state, the potential energy V of the, so this is V is what? Potential energy in deflected state. U was what? Potential energy in the equilibrium state or original state. Right? So in deflection what happened? This will decrease by Py. So that's why in deflected equilibrium state, V will be equals to minus of Py. Okay. A deflected equilibrium system total potential energy, that TPE, is now defined as the sum of its internal or strain energy and the potential energy of the applied external force. So either whatever they have the internal energy, or you can see the strain energy, because after getting expanded they stored some energy, that strain energy or their internal energy, plus what? The potential energy of the applied external load. So because of the applied load, what will be the potential energy? So here what is the potential energy because of applied load? That is Py, that is minus Py. V is minus Py. So total potential energy is equals to strain energy plus that the potential energy because of the applied load, external applied load. So U plus V. Right. The strain energy already we had seen, that is 0 to Y P divide. This was the strain energy we earlier also seen this one. And V is minus Py. So what we will get? TP as 0 to Y P dy minus Py. So this will be the total potential energy. Okay. So now just see, first apply the same principle of conservation, that one. The potential energy of all the loads in a general system consisting of load P1, P2, P3, so on. Earlier also we found for that particular only. That is what? Pn producing corresponding displacement, that is displacement in the direction of the load 1, 2, 3, so on, and that is delta 1 at point 1, delta 2, delta 3, so on, delta 1. So at point 1, delta 1, at point 2, delta 2 is because of P1 load, delta 1, P2, delta 2, P3, delta 3, so on, Pn, delta 1 is because of load Pn, the displacement is delta n. So then what will be the potential energy? That V is V of R, means what if V is V1 plus V2 plus V3 plus so on Vn. What is V1? V1 will be minus Py, right? So V is minus Py. So V1 will be what? Minus P1 Y1, or what we are taking delta 1. So P1 delta 1. V2 will be equals to minus P2 delta 2. V3 will be equals to minus P3 delta 3. So on, Vn is equals to minus Pn delta n. So instead of writing this again, right, simply here minus, because that V is minus Py, right? So minus of Pr delta r. Now put here r equals to 1. So minus P1 delta 1. Here. V2 minus P2 delta 2. V3 minus P3 delta 3. V4, right, minus P4 delta 4. Vn minus Pn delta n. So this is the what? Potential energy because of the external applied load. Right. So substitute in TPE equation. What was TPE equation? And the system of total potential energy is given by what? TP is U plus V. Okay. What is U? That we know that 0 to Y P dy in terms of that. And now we got V as for the whole system, that many system when many loads are acting. That was, this is for one particular load, right? That P load is acting somewhere, and then we found. But when many loads are acting on that system, but internal energy will be same because of that only. Sorry, strain energy. So strain energy again 0 to Y P dy will be there, but potential energy because of those mass will be this one, sum of all this value. Okay, so just the V, previous one was for the one load, and this is for n number of loads. So the total will be U plus V again. So U and V is what? R equals to 1 to n of minus PR delta R. Okay, so this will be the total potential energy method. So now just see what we have to do is what? First find strain energy with the general method, whatever is there. Then go for the finding potential energy because of the applied load. So how many load is applied? That many times you have to find the potential energy because of that load, right? And then what? Just add all the loads and add with the strain energy load. That will be the total potential energy. And with that, you can find the deflection or whatever. If the total potential energy is required, then you can find that one. That's all, right? So in that way, you have to do. Next is flexibility method. So in this method, just very simple is that any method you can use what we used earlier in any method. Only the thing is what? According to your choice, you can just release the number of members. Okay, so just here. A different approach to solving a statically indeterminate. So here, this we can use for indeterminate structure, means that very difficult to find the solution or we cannot get easily solution. And that's why we had seen that by energy method, what we can do, whatever the complex structure is there or which we cannot find by the normal method, that also we can find. So in that one more, this one is there, if a statically indeterminate structure which we cannot find by the other method, or right, then what you have to do, just see here. So indeterminate beams and frames is to release the structure. Okay, so now whatever the original structure is there, release some member, release the structure, removing redundant member. Redundant member means right, or support until the structure becomes statically determinate. Means remove those members which does not support or which does not have any or distribute any load in that structure. Remove that one. Remove till that structure becomes statically determinate. Now, once it's statically determinate, you can apply any of the method. Either unit load method, total potential energy method, Rayleigh-Ridge method, any method. The thing is only first for the complex member, what you have to do, you have to, from the indeterminate structure, you have to make determinate by removing the members that what? Redundant member, means which does not carry any load or which does not contribute the load, or say the loads, right? That member start removing. Once that becomes the determinate structure, then it's easy. Now you can go for any other method. So just here, the displacement of a point in the release structure is then determined using a method such as unit load method, or you can use not only such as unit load method. So whatever method we can see, we had seen all the method we can use once that structure becomes statically determinate, either unit load, total potential. Just now we had seen in the previous video the total potential energy method, right? In this video itself, the total potential energy method. In previous video we had seen that Rayleigh-Ridge method, unit load method. So whatever the methods are there, once that structure becomes statically determinate, we can use that one. So flexibility method is, there is no special method, only it's there what? For statically indeterminate structure, you can just make it the statically determinate. And once it becomes determinate, by removing only the redundant member. Make sure by removing the redundant member only, not all the member from anywhere. Because if you will remove the member from anywhere, then load carrying or load distributed capacity will get decreased. Then we cannot get the actual value. So only the redundant member should be removed to make it the statically determinate. The actual loads on the structure are removed, right? And unknown forces are applied to the points where the structure has been released. So where the structure has been released, what happened? If actual load is there, just remove that load and apply the what? Unknown forces applied to point, right, at that point. The displacement produced by these unknown forces must be the same as that in the release structure based on the compatibility. So what happened? Once actual load will apply, then they will have some displacement, right? So once just remove that structure, means in the initial structure, right? Suppose this is the structure, right? So now what happened in that member, whatever load is, suppose here load is acting, right? So because of this load, whatever the displacement will be there, right, in these things. Now just removing this redundant, suppose this member is redundant or this member is redundant. We are removing this member, right, and applying the force, the displacement should be same. Then only we can. So just here, displacement produced by these unknown forces must be the same as that in the released structure based on compatibility, right? So that displacement should be same. That also you have to take care for that unknown forces. The undefined forces are then obtained using the flexibility method. So now once you have the undefined force, by flexibility method you just find. Once you have the, either you can use any method, either unit load method, that total potential energy method, from that you can find. With the same thing you have to do for that unknown method, because first you know the total potential energy is how much because of that load. Now what, just remove that one, apply the energy method, sorry, apply the unidentified load or unknown load, and because of that unknown load find equate both, because that displacement should be same. Displacement is same, is they must have the same strain energy, right? Just apply that force, equate it, and then find the unknown forces. Okay, so just see quickly once again this method. So we are now, next method is what, the total potential energy method. So in that what we will do, how much potential energy they will have, that we have to find. So first, only when one normal mass system is there, just for spring mass, here at the equilibrium this was having potential energy because at a height h, so this having mass mgh. Now this got stressed or get displacement or strained, so it's getting displaced by y. So now this total distance is how much, h minus y. So now this will have how much potential energy, mg into h minus y. So by what amount this will lose, mg y, right? By y amount this will lose, that is their potential energy. Now that what happened to that potential energy, that converted only into the kinetic energy. Okay, so now what happens, so this will be the loss of what, b equals to minus of py is the loss in that one. So now if suppose that p load is acting, where p is equals to what, mg. So now the total potential energy will be what, strain energy plus potential energy. So total potential energy will be equals to u plus v. So what is u, that already we are seeing that u is 0 to y, p dy, and potential energy is minus p into y. So this is for one load, one mass where it's acting, that one load p is acting that time. If system of mass is there, when many loads are there, then what happens? So then unit that strain energy, again by same method you can find. Potential energy we have to find by different method. How? So just see here, the potential energy, that because of n number of load, p1, p2, p3, so on, acting at point 1, 2, 3, and because of p1 the deflections are delta 1, because of p2 delta 2, because of p3 delta 3, so on, because of pn delta and deflections are there. So now what will be the potential energy, that we know that potential energy that v is minus of py, where y is the displacement, here displacement is delta 1. So what happened, v1 will be equals to minus p1 delta 1, v2 equals to minus p2 delta 2, so on, right? So vn equals to minus pn delta n. So instead of writing this, just simply r equals to 1 to n minus of pr delta r, right? Now just put this value, you will get what, the total potential energy. So total potential energy will be equals to what, u plus v, which is equals to u plus v is now here r equals to 1 to n minus pr delta r. So this will be the total potential energy of the system having n number of mass, or sorry, n number of load is acting on that system. Okay, next is flexibility method. So flexibility method is nothing, it's just simple, whatever the statically indeterminate structure is there, that you have to remove the redundant member. Remember, redundant member only you have to remove, right? And make it what, statically determinate. Once that is statically determinate it will be, then you can apply any of the method, either total potential energy method, Rayleigh's method, unit load method, and you can find that. Okay. So now just see how the actual load on these structures are removed and unknown forces are applied. So first, after removing this, now apply, just remove all the actual load were acting, and then apply the unknown forces are applied to the point where the structure has been released. So wherever the actual load is acting, just remove that one, right? Now from in this structure, right, suppose load is acting here, right? So now we are removing this load at this point. So apply here that unknown forces, remove this force and apply unknown force here, or apply unknown force here or in any direction. That depends on this requirement, that only, right? To the points where the structure has been released. The displacement produced by these unknown forces must be same as in this released structure. So now because of this also, whatever because of this will be there, that also must be same from the conservation of energy. Now just equate these two, you will get the unknown forces by the flexibility method. So that is only the flexibility method. Okay. So in this, if you have any doubt in this method or how to use that one, you can just comment on the video or you can contact me. I will clarify your doubts. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.